Welcome back to my channel, guys. This is Subject-o-Phile and this is my third video on this channel. The video will be about a very interesting question on rotational mechanics from one of the toughest physics exams of the world, that is Indian National Physics Olympiad INPhO 2020. The question number was 5 and the marks allotted was 20, so which is huge. So let us, before getting into the question, let me tell you few things that I have posted the link of the official solution that was uploaded by HBCSC and also a YouTube link of the detailed explanation of that approach which was given in the solution. It was done by my physics teacher, Mr. Ujjwal Agarwal, and he uploaded the video of that in his own YouTube channel. I have given the link of that video in my description box. You can go check it out. So my approach would be a little different from all the approaches that you are already seeing in the YouTube. Why so? Because I have actually gone and used the concept of impulsive forces to solve this question. In the market, you will find the solution in the form of finding the direction of conservation of linear and angular momentum, and then you can easily solve that question. But I am using the most basic and fundamental concepts of collision, that includes the use of impulsive forces and impulse. So uh, this process might be a little long, but this will actually teach you the most basic and fundamental concept of impulsive forces, which you might need in many questions of collision where you would not be able to find the direction in which you have to conserve linear angular momentum, because either it does not exist entirely or it is very tricky to find. So it will save your time in those questions. So as I've been saying about collisions, let me ask you, what do you actually mean by collision? Does it necessarily mean that the two objects must be in contact to collide? No, guys. Objects does not need to be not need to come in contact for collision. Rather, it is a kind of interaction between two objects that tends to cause deformation or reformation in both the objects involved. So, the forces that are involved in a collision can be both contact and non-contact forces. Now, let's understand what is impulsive forces that I have been telling you guys for so long. So, it is a force that is acting in a very short period of time but have a large impact on the system. Uh, Obviously, non-impulsive forces can be neglected in presence of impulsive forces during the same time duration, because the non-impulsive forces are almost insignificant and of low magnitude. The values are of low magnitude. So the IFs can only be balanced by IFs and not NIFs, as it is insignificant. So example of IFs: normal force, mean frictional force, tension. Why I have written may or may not be, you will understand that in the next slide. And the examples of NIFs is weight, spring forces. These are always non-impulsive forces that I have written. That's why I have written always. Now impulse differs from impulsive forces. Why? Because impulsive forces is force which is actually mass times acceleration acting in a very short period of time, but impulse is actually the change in momentum of a particle. It gives us idea about the change in momentum of a particle. Now this graph exactly depicts the profile of impulsive force and non-impulsive force during a very short interval of time between from 0 to capital T seconds. Okay, now let's move into the next slide where I have written, for translation, the impulse J, which is denoted by J, is actually F dot dt. That is why I am saying that impulse gives us an idea about the change in linear momentum or angular momentum. Here it is for translation, and here it is linear momentum delta P. So FIF vector is the impulsive force vector. Now for rotation, the same thing happens, just we have to take a cross product with the radius arm, that is r cross j, giving us the tau dt, tau dot dt, integration of tau dot dt, which will give us eventually change in angular momentum delta L vector. So tau if vector is the impulsive torque vector. Now we consider the collision of two blocks. Then obviously we can say the normal force which is acting between the two blocks, the normal force which is acting between the two blocks will become impulsive because it is acting for a very short duration of time during the collision only. But the normal forces between the blocks and the ground are non-impulsive because it is acting for the entire the time duration of the entire motion, and it has a constant magnitude, as well as the weights. That is why I have said weights and spring forces of any block or of any particle is a non-impulsive force, as it does not change during the entire motion of the time, as long as it is in the same gravitational force field. Though we are not considering the change of gravitational force field in our questions. So let us move on to the next slide. Now let's come back to our question and try to solve it. So what does our question says? The following is the top view of an assembly kept on a smooth. Now let me take the laser pointer for you guys so that it will be easy. So the following is the top view of an assembly kept on a smooth horizontal table. A massless, inextensible string of length d lies with one end fixed while the other is attached to one end of a uniform rod of length l. The system is initially at rest with the rod aligned along the x-axis and the string stretched to its natural length at an angle with the negative y-axis theta. So cos theta has been given as 1 by 3. At a certain instant, a bullet of the same mass m as the rod and negligible dimensions is fired horizontally along the positive y direction. The bullet hits the rod at its right end with velocity v0 and gets lodged in it, the impact being nearly instantaneous. What is the tension T in the string immediately after the impact? Assume the string does not break. So we have to find tension T in the string in terms of obviously the given parameters in the question, which is v0, L, and D. Okay, so let us move into the solution of this question. Now first let's focus on the motion of the rod. What can happen after the collision? So the bullet collides and gets embedded in the rod. As you can see, it comes with a velocity v0, and there is a tendency of the rod to rotate about point A. Obviously, after the collision, it will have a tendency to rotate, but this will not happen because the string becomes taut immediately after the collision, and that is why it prevents the tendency of the rotation. So the string becomes taut. Now, if it rotated, then the string would have broken, but since it is mentioned in the question the string does not break, so the rod will not, it is not possible for the rod to rotate, so the string will become taut here. Now we have mentioned some given parameters: AB equal to L, OA equal to D, cos theta equal to 3, 1 by 3. So obviously sin theta becomes 2 root 2 by 3. Now since we mentioned that during the collision these forces are acting for a short period of time, so the impulsive forces between the rod, bullet, and the string uh, is actually, like, the forces acting between them is actually impulsive in that time duration. Alright, so this is making the string taut as well. Now let's focus on the impulsive forces acting on the string rod bullet system. See, the impulsive forces which is acting, first let us consider the collision of the rod and the bullet. So there is an impulsive force acting between them due to the collision. Now I have considered the components. Why? Because because we don't know exactly the motion of the rod, in which direction it is moving. So it might be moving as entirely like in a direction like this. Alright, so it will have a velocity in y direction as well as an x direction. So since the bullet gets embedded here in the rod, so the bullet will also have a velocity in x direction as well as in the y direction, right? That is why, who will be providing this velocity in the x direction? Obviously the impulsive force Jx, because initially it had no velocity in the x direction. So an impulsive force Jy, a normal impulsive force Jy will be acting like this, and an impulsive force Jx. To counterbalance it, there would be an impulsive force Jx in this direction on the rod and Jy in this direction. Okay, this C is the new center of mass of the rod and the bullet system, because both was of mass m. So the center of mass would be lying in between point O and the end B of the rod. And obviously the tension in the string also becomes impulsive, so let us say it is Jt, and it has two components, Jt cos theta and Jt sin theta. Now let us assume the velocities of point O, or the center of mass of the rod, is Vy and Vx in the xy direction respectively, and of the center of mass of the entire rod bullet system is Vcmy and Vcmx respectively. And obviously the bullet, since it gets embedded in the end B of the rod, so it will obviously have whatever velocity NB of the rod has. It will be the same as same. The bullet will carry the same velocity, right? So I have said that the final velocities of the bullet after the collision becomes VBY in this direction and VBX in this direction. And obviously, due to the tendency of rotation, the rod will have a angular velocity omega in this direction. Now let's find the relation between the velocities of different points on the rod. So in x direction, there will be no change in velocity because there is no effect of rotation of the rod. So it is Vcmx equal to Vx equal to Vbx. But in y direction, there will be effect of rotation of the rod because there is a angular velocity omega. You obviously know how to write it because since with respect to the center C, center of mass C of the system, point O will have an also have a speed L omega by 4 in this direction. This was L by 2. C is in midpoint, so this is L by 4, so L omega by 4 in this direction. So the net speed of O in respect to ground frame will be Vy minus L omega by, like the net speed would be Vcmy minus L omega by 4. Alright. So Vy equal to Vcmy minus L omega by 4. Vy is the speed of point O with respect to ground frame. Similarly, I can write the velocity of end B of the rod, and then we can find the relation using these two equations. We can find the relation between BBY and BY. These will be needed in the subsequent solution. Okay, so this is due to effects of rotation of the rod. Now, the important thing is, since the string is taut, so relative velocity of the string along OA or CA, whatever you might say, is 0 because this is the string constant that we always use constant equations in NLM. The similar thing it is here also, because if the relative velocity would not have been 0, there would be an extension of length, which means the string would break, right? So point A can only have a velocity along the direction perpendicular to OA, which means momentum does not change in that direction, i.e. it is conserved. Okay, so you also find the direction in which the momentum of this entire system is conserved, that is in a perpendicular direction to the string. But since we are not using that approach here, we do not need this information. Okay, let's focus on point A of the rod and try to analyze the velocity of that point. Since I said the net velocity has to be in perpendicular direction to the string, so we assume that the velocity is Va in ground frame. So with respect to O, it will have Vy and Vx, and also with like since the ground speed of O is Vy and Vx. So when we write the ground speed of A, we write the ground the velocity, the vector of the ground speed of A would actually be the ground speed of the ground velocity of point O plus the velocity, which is velocity of A, which is respect to the point O. So with respect to point O, the A moves in a circle, so it will have a velocity L omega by 2 in this direction, right? And the Vy and Vx is already there. So we use the string constant first, and then we can find this equation Vy cos theta, like Vy cos theta plus Vx sin theta must be equal to L omega by 2 cos theta in order to maintain relative velocity as 0 in this direction along the string. So put the values of sin theta and cos theta, and then we simplify and we get the velocity of Vx in terms of the value of Vx in terms of Vy and omega. This will be very necessary, and that is why I have highlighted it in a green box. Now the net velocity which appeared perpendicular to the string would be L omega by 2 sin theta plus Vx cos theta minus Vy sin theta. You can easily see from the diagram L omega by 2 sin theta plus Vx cos theta minus Vy sin theta. And if we simplify it, we can get an expression of Va that will be needed later. Okay, so let us move into the next part, which is writing the impulses on the particles, bullet and rod. The fun thing is that you can exactly solve it by the way you solve NLM questions by drawing FBD, and then algebraically manipulate the impulses to get the change in momentum of those particles. Similarly, for bullet, you can see that in the y direction, the impulse was jy, which is opposite to the direction of change of the velocity, because initially it was v naught in this direction, then finally it became vby for the bullet. So what should have been the change in momentum should have been final minus initial, but here it is initial minus final because jy is in opposite direction, so the negative sign has been compensated here. So you put the value of vby and then you get jy as this. Okay, now jx in the x direction is similarly mvbx, which is the velocity is gaining in this direction, and it is equal to mvx. So Now let's move into the next part, which is the considering the translational motion of the rod. In the y direction, the impulses of jy and jt cos theta in the same direction. So we add them and we write vy minus 0. Because why we are considering vy? Because we are considering the rod only. So we consider the velocities of the center of mass of the rod only. That is vy and vx. And initially it was 0. So vy minus 0. We solve it and we put the values of jy and sin theta and jy and cos theta, and we can easily find the equation, that is jt by 3 plus mv naught minus ml omega by 2 equal to 2mvy. Now in x direction we have jt sin theta minus jx equal to mvx minus 0. Alright, so we can again further simplify it in this way, and then we can find jt by 3 equal to mvx by root 2. We keep these equations as it is, and then we move to the next part, which is we considering the rotational motion of the rod. We see that there are two torques, two impulses which is providing the torque. That is the jy and the jt cos theta, and both has a radius arm of L by 2 from the center O, center of mass of the rod. So we write the torques, we write the actually we write the moments, which is jy dot L by 2 minus jt cos theta dot L by 2, which is equal to ml square by 12 omega, because because change in angular momentum is ICM omega f minus omega 0, omega final minus omega initial, but omega initial is 0, so it is minus 0. And the ICM about the rod, center of mass of the rod, is obviously ml square by 12. So I have written ml square by 12 here. By further simplifying it by putting the values of cos theta and also putting the values of jy and jt. From where did we get the value of jt? Because we had the equation in the last slide, if you remember. Then we have obtained the value of jt from there, and we have put it in this equation right here to further simplify and get the value of vy in terms of omega and v naught. So we got the value of vx, and now we have got the value of vy. We are highlighting it because it is needed in the later portion. So let us come back into that side of where we were discussing about the translational motion of the rod. We actually put the value of jt by 3 into this equation right here, and then we can solve and simplify it to get this equation right here, mvx by root 2 plus mv naught minus ml omega by 2 equal to 2mvy. Okay, now we already have the values of vy and vx, so we put the values of vy and vx in this equation and also cut the m from all the sides of the equation, and then we simplify it further. It is not a much longer process, it is easy to simplify if you are good in calculations, and then we get the first breakthrough in this problem, that is the value of omega in terms of v naught by L. Such a simplified values, you see, such a big question and such a simplified value of omega, that is v naught by L. So that is very important breakthrough. That is why I congratulate all of you that you have got this value of omega, which is we needed to solve each and everything in this equation. So now we can get the parameters, the values of all the other parameters like vy, vx and va in terms of v naught. So vy equal to 5 v naught by 18, vx equal to v naught by 9 root 2, va equal to v naught by 3 root 2. Okay, so we will be requiring all these values afterwards. So now let's focus on the forces that is acting on the rod bullet system. Now we know any forces acting on this entire system would be acting, would be producing acceleration on this system, on the center of mass of this system, right? So we have to now have to consider the center of mass of the rod bullet system, not the point O, rather the point C. Okay, so the forces, obviously the net forces, the external forces that is acting is the tension T on the string, which will be actually producing an acceleration ay and ax in the x and y direction respectively for the center of mass, and also provide angular acceleration alpha in this direction due to the torque it generates. So using the force equations, now the entire mass of this system is 2m, not m, because we are considering the rod bullet system together. So we write the force equations in the respective directions, and we finally get ay and ax in terms of t and capital T and small m. Now we consider the rotational effects. T cos theta dot 3l by 4, because this radius arm is 3l by 4 from the center of mass, and it is ICM alpha. Now for the center of mass of this system, the moment of inertia of the center of mass of this entire system has contribution from the moment of inertia of the rod, as well as the moment of inertia of the bullet at this point. How we will get that? For the bullet is very simple. It will be m into L by 4 whole square. But for the rod, we use the parallel axis theorem, where we know the moment of inertia of the rod at this point O. The center of mass of the rod is ml square by 12, but we have to shift it by L by 4. So ml square by 12 plus m of L by 4 whole square. This gives us the contribution of the rod, and this is the contribution of the bullet. So we get the entire ICM as 5 ml square by 24, and we put it here in this equation. By further solving, we easily find the value of alpha in terms of capital T and M. This is the second breakthrough of this equation. So we actually find the value of omega, and then we find the value of alpha. Very good. Now let us move into the next slide, where we again come back to the point A, but now this time we analyze the accelerations of the point A with respect to ground and its tendency of motion. So obviously, with respect to ground, center of mass has the accelerations ay and x, which will remain. But with respect to like center of mass, there was an angular velocity omega, for which this will have a pseudo acceleration. Like, since point A with respect to center of mass is moving in a circular motion with respect to the center of mass, and since the center of mass is moving with an angular speed omega, obviously we have learned that there will be a centripetal force required, or which is a pseudo force with respect to, and whenever we are thinking of, whenever we are analyzing the motion of point A with respect to center of mass, there will be a pseudo force of omega square 3L by 4, right? So that is why this omega square 3L by 4 term is coming, as well as since there was an angular acceleration alpha. So with respect to center of mass, the point A will also have an acceleration 3L alpha by 4 in this direction, right? So these are all the four accelerations in the respective directions for point A. Now we already have the net velocity of point A here, VA in ground frame. But see, since the string is taut, what our general common sense says, that this point A we have a locus of a circular path with respect to the point of suspension of the string, which is point O. So this velocity Va, which is tangential to this path, will actually provide the radially centripetal acceleration needed for point A to remain in this circular path. So this radially centripetal acceleration should be along the direction of the string, and it should be given by this net velocity Va, which is the tangential velocity. So with respect to point A, and each and every point of the rod moves in a circle, and the point A itself moves in a circular path with respect to the point of suspension O. And here I have already mentioned that this is due to the pseudo force m omega square r experienced by point A with respect to the center of mass. So this is the centripetal force, and the acceleration is omega square 3L by 4. So we again closely analyze this entire diagram that we drew there, the accelerations of point A. Now, since as I said, it has to provide these accelerations has to provide a centripetal force in this direction, centripetal acceleration in this direction for point A to be able to move in that circular path. So we write ay cos theta plus ax sin theta plus 3 L alpha by 4 cos theta minus omega square L 3L alpha by 3L by 4 sin theta. That should be equal to Va square by d, because the radius of this path is capital D. So we write the components of all these accelerations along the string or along the direction OA to get Va square by d. Now further solving it by putting the value of sin theta and cos theta, and also we have the values of omega, ay, ax, alpha and Va. We put all these values right here that we have got in the previous slides to further simplify it, and so that we are only left with those terms that are present in the question, that is capital T, small m, V naught, capital L, L capital D. So you can easily guess that we are very near to the end of the solution of this question. So by further simplifying it, and then we have to cancel the denominator and numerator by the common terms, then we can easily get, see, we are almost there as I've already said. So simplifying further, we get this, and then by shifting it to this side, we finally have the solution of our question, the value of tension, that is 5m v naught square by 4 in third brackets 1 by 18d plus 1 by L root 2. So very congratulations to you guys that you have already obtained 20 marks a very big portion of marks in that paper, which consists of only 6 questions to be solved in 4.5 hours. So it is a great achievement for you guys. Congratulations. So let's put our answer in the space provided by them. So see, it looks so good, right? So we are at the end of the solution of this video. I hope you have liked the video, and I hope that I'm able to teach you the concepts of impulsive forces and you have understood it right away. And I think I have somewhat been able to clear your fears of the chapter of rotational mechanics, because this chapter is very good and it's very fun, and it's a summary of the entire mechanics. So there is nothing to get afraid of this chapter. Rather, if you learn the concepts nicely, if you understand it, and if you practice hard, this chapter can be the most beautiful chapter of physics, and you might eventually fall in love with it, as it is one of my favorite chapters in entire mechanics. So thank you guys. If you have liked the video, please subscribe my channel, share it with your friends, family members, and whatnot, like future aspirants, your brothers, sisters who might need this channel to get a guidance for their competitive exam preparations. Please like the video, share and subscribe my channel. Thank you. Till then, goodbye, and meet you all in the next video.